To understand how SDN works, it is best to think of it as a request and command system that operates in a continuous loop. It transforms a network from a collection of independent devices into a single, programmable entity. Here is the step-by-step summary of the SDN workflow. 1. Centralized observation. In a traditional network, a router only knows about its immediate neighbors. In an SDN environment, the SDN controller uses southbound protocols to constantly gather data from every switch and router in the network. It builds a real-time global topology map that includes link status, traffic congestion, and hardware health. 2. Policy definition. The intent, an administrator or an automated application, via the northbound interface, tells the controller what it wants the network to do. This is called intent-based networking. Example, ensure all traffic from the finance department is encrypted and takes the path with the lowest latency. 3. Path calculation and logic. The controller analyzes the request against its global topology map. Instead of every router running complex math individually, like OSPF or BGP, the controller calculates the optimal path for the entire network at once. 4. Rule distribution, flow tables. Once the path is decided, the controller pushes specific instructions down to the hardware via the southbound interface. It doesn't send a routing table, it sends a flow entry. A flow entry tells the switch, if a packet matches these criteria, IP, port, VLAN, perform this action, forward to port 3, drop, or encapsulate. 5. Data plane forwarding. The physical switches, the data plane, receive the packets and look them up in their local flow tables. If there is a match, the switch forwards the packet at wire speed without asking the controller. If there is no match, a table miss, the switch sends the first packet of that new flow to the controller. The controller decides what to do and sends a new rule back down. The operational cycle. Step action responsibility. 1. Collect, monitor traffic and topology controller, via southbound. 2. Request define business needs / apps application layer. 3. Decide translate needs into flow rules control layer. 4. Enforce push rules to hardware southbound interface. 5. Forward move packets based on rules infrastructure layer. Key technical advantages in operation programmability. You can write a script to change how the network handles traffic at 2 a.m. without touching a single CLI. Traffic engineering. You can move heavy data backups to an underutilized fiber link to keep the main link clear for VoIP calls. Security. If a switch detects a cyber attack, the controller can instantly push a drop rule to every switch in the network simultaneously to quarantine the threat. Advantages of SDN. Software-defined networking, SDN, provides a transformative shift from hardware-heavy management to a software-centric model. Here is a summary of its advantages across your specified categories. 1. Centralized control. In traditional networks, every router is a silo that must be configured individually. SDN moves the brain to a central SDN controller. Global visibility. Administrators have a bird's-eye view of the entire network from a single dashboard. Consistent policy enforcement. You can push a security or routing policy to thousands of devices simultaneously, ensuring there are no configuration gaps or human errors. Simplified troubleshooting. Because the controller monitors all links in real time, it can identify a failure point instantly rather than an engineer having to log into multiple boxes to find the break. 2. Flexibility and adaptability. SDN allows the network to be as dynamic as the applications it supports. Dynamic traffic engineering. If a primary link becomes congested, the controller can automatically reroute low-priority traffic to a different path to preserve quality for critical apps, like VoIP or Zoom. On-demand scaling. Network capacity can be spun up or shifted digitally to meet sudden spikes in demand without physical hardware changes. 3. Programmability. This is the core of infrastructure as code. Automation. Using northbound APIs, developers can write scripts that automatically reconfigure the network based on specific triggers. Example, if it's 2 a.m., move all backup traffic to the 400G core link. Vendor interoperability. Because SDN uses open protocols, like OpenFlow or NetConf, you can manage hardware from different vendors, Cisco, Juniper, Nokia, using the same software commands. 4. Network virtualization. SDN allows a single physical network to be carved into many independent virtual networks. Multi-tenancy. In a data center, different customers, tenants, can have their own completely isolated networks on the same physical cables. Microsegmentation. You can create security bubbles around specific workloads, preventing a breach in one virtual machine from spreading to the rest of the network. 5. Faster innovation. SDN breaks the vendor lock-in cycle that traditionally slowed down progress. Decoupled cycles. You can upgrade your network software, the control plane, to add new features without waiting for hardware manufacturers to release new physical routers. Sandbox testing. Developers can create logical versions of the network to test new services or configurations in a safe environment before deploying them to the live production fiber. 6. Cost efficiency, CAPEX and OPEX. SDN fundamentally changes the economics of networking. CAPEX savings. By moving intelligence to the software, you can use white box or commodity hardware, basic, high-speed switches, instead of expensive, proprietary feature-rich boxes. OPEX savings, automation reduces the man-hours required for manual configuration and cable pulling. Resource optimization, better traffic management means you don't have to over-provision, buy extra bandwidth you don't use, just to handle occasional peaks. The software manages the load more efficiently. Comparison summary aspect advantage control one central brain instead of 1,000 separate ones. Flexibility the network bends to the needs of the apps, not vice versa. Programmability network management via code, not manual typing. Virtualization many logical networks on one physical fiber. Innovation software speed versus slow hardware cycles. Cost use cheaper hardware and automate expensive human labor. SDN use cases in 2026, SDN is no longer a theoretical concept, it is the backbone of almost all modern high-speed infrastructure. By decoupling the control logic from physical hardware, it enables specific, high-value use cases across different network domains. 1. Data center networking, east-west traffic and AI in modern data centers, the majority of traffic moves between servers, east-west, rather than out to the internet, north-south. Automated provisioning, when a developer spins up a new virtual machine, VM, or container, the SDN controller automatically configures the virtual switch, assigns the VLAN, and sets security rules without human intervention. AI cluster optimization, in 2026, SDN is critical for AI training. Controllers monitor link utilization and dynamically reroute elephant flows, massive data transfers between GPUs, to prevent network congestion that would otherwise stall AI model training. Microsegmentation, SDN enables granular security where a firewall policy is applied to each individual VM. 2. If one server is compromised, the SDN controller instantly quarantines it, preventing the threat from moving to the server right next to it. 2. Carrier networks, traffic engineering and IPO-DWDM telecom carriers use SDN to manage massive, geographically dispersed fiber networks. Multi-layer restoration, as discussed with IPO-DWDM, SDN controllers can see both the IP layer and the optical layer. If a fiber is cut, the controller doesn't just wait for a router to time out, it immediately recalculates a new optical path and reconfigures the ROADMs. Bandwidth on demand, carriers can offer calendared bandwidth. A bank might need 10x more bandwidth at midnight for data backups, the SDN controller automatically schedules this increase and reverts it at 6 a.m. 3. Campus and enterprise networks, SD1 and BYOD for schools, hospitals, and corporate offices, SDN focuses on user experience and policy. SD1, software-defined WAN. This is the most popular SDN use case for enterprises. It allows a branch office to use a mix of expensive MPLS and cheap broadband. The SDN controller monitors the quality of each link and sends Zoom calls over the cleanest path while sending email over the cheapest one. Identity-based access, when an employee moves from their desk to a conference room, the SDN controller follows them. Their security permissions and VLAN access remain the same regardless of which physical Wi-Fi AP or wall jack they plug into. 4. 5G mobile networks, network slicing. SDN is the foundational glue that makes 5G work differently than 4G. Network slicing, SDN allows a carrier to carve one physical 5G network into multiple slices. One slice can be optimized for ultra-low latency, for self-driving cars, while another is optimized for massive throughput, for 8K video streaming, all running on the same hardware. CRAN, Cloud Radio Access Network. SDN helps centralize the processing of cellular signals in the cloud, allowing cell towers to be slimmer and more energy efficient while the brain of the tower runs on a central server. 5. Cloud networking, hybrid and multi-cloud. Cloud providers, AWS, Azure, Google Cloud, are essentially massive SDN implementations. VPC, virtual private cloud. Every time you create a private network in the cloud, you are using SDN to create a logical network that doesn't exist physically. Intercloud transit, SDN controllers manage the complex tunnels, like VLAN, that connect an on-premise data center to a public cloud, making them appear as one seamless network to the end user. Use case comparison matrix. Domain primary focus, key technology, data center speed and security. Microsegmentation, VLAN carrier efficiency and uptime. IPO-DWDM, optical restoration. Enterprise cost and connectivity. SD1, zero trust access. 5G mobile service variety. Network slicing, edge computing. Cloud agility and multi-tenancy. Virtual private clouds, VPC. SDN versus traditional networking. The transition from traditional networking to SDN is often compared to the transition from a fleet of independent vehicles to a centrally managed high-speed rail system. The primary difference lies in the architecture. Traditional networks are distributed, meaning every device makes its own decisions. SDN is centralized, meaning one brain dictates the behavior of all devices. Comparison matrix, traditional versus SDN aspect. Traditional networking. SDN, software-defined, distributed, each device centralized. Decisions are made by a router/switch, has its own brain control central software controller, hardware just and makes its own forwarding follows orders. Decisions. Manual, admins must log into each orchestrated, managed through a management device individually, CLI, to make single pane of glass or dashboard that changes. Controls all devices at once. Rigid, limited by the hardware's dynamic, traffic flows can be changed in flexibility fixed capabilities and slow manual real-time via software to adapt to new updates. Needs. Local, each device only knows its global, the controller has a bird's-eye network immediate neighbors, hop-by-hop view of the entire network topology and view. Health. Reactive, relies on manual scripts proactive, built-in APIs allow the network automation, Python/Ansible, to push static to self-configure and heal automatically configs. Based on policies. 1. Control, decentralized versus centralized traditional, if you want to change a route, every router in the path must run a protocol, like OSPF or BGP, to agree on that change. It is like a group of people trying to agree on a route using separate maps. SDN, the SDN controller acts as the only map holder. It calculates the path and tells every switch exactly which turn to take. 2. Management and automation traditional, configuration is box by box. To update 50 switches, an admin might have to enter the same 10 commands 50 times. This is slow and prone to human error, typos. SDN, uses APIs, northbound and southbound. You define a policy once, e.g., give all video traffic priority and the controller automatically pushes the necessary technical settings to every relevant device in seconds. 3. Network view and intelligence traditional, a switch only knows what is directly plugged into it. If a link 3 hops away is congested, the switch might not know until the packets start dropping. SDN, because the controller sees the entire network, it can detect congestion on the other side of the country and reroute traffic before the user experiences a slowdown. 4. Flexibility and innovation traditional, adding a new feature, like a new security protocol, usually requires buying new hardware or waiting for a massive firmware update from the vendor. SDN, you can write a new piece of software, an app, for the controller to add a feature. This allows companies like Google or Amazon to innovate at the speed of software development rather than hardware manufacturing.